Hello, everyone. Welcome back to this webinar series from Usomi. I'm Gennaro Danna. I'm a neuroradiologist at ASST Ovest Milanese in Legnano near Milan, Italy. And I'm very happy to introduce this second session. And as usual, I have the pleasure to have with me in the moderation zone my favorite partner in crime for the webinar, Pınar Yılmaz. She's a radiology resident from Erasmus Medical Center, Rotterdam, the Netherlands. Very teached about the AI and informatics, and as usual, thank you so much, Bayer, for supporting us in this initiative. But now I give the virtual microphone to my partner in crime, Pınar Yılmaz.
Thank you very much, Gennaro. Likewise, you're also my favorite moderator of the group. Welcome, everybody. We have Peter van Ooijen with us. Very, very much pleasure to have him. He's an associate professor in AI and medical imaging at the Department of Radiation Oncology in the University of Medical Center Groningen. And he also coordinates the machine learning lab of the Data Science Center in Health over there. Furthermore, he's an author of many publications and book chapters, including our book in the Usomi book series, Imaging Informatics for Healthcare Professionals. And also, last but not least, he's also becoming our incoming president of Usomi. So big clap for that. If you have any questions, please write them in the Q&A box and we will discuss these at the end of the presentation. So for now, Peter, the floor is yours.
Thank you very much, Pınar and Gennaro, for the introduction. Yeah, looking very much forward to becoming the president of the Usomi tomorrow at the General Assembly. We will have that happening, and I'm looking forward to working with all of you in the future, in the coming years, to even build up the European Society of Medical Imaging Informatics even more. As you may hear from my voice, I've got a bit of a cold, so I hope that I can reach the end without coughing too much, but we'll see how it goes. I was asked today to tell you something about the IT infrastructure to deploy artificial intelligence. I was invited by the Usomi and Bayer to give this presentation, and when you see this title, you might ask yourself, why is this relevant as a topic? Well, in the development and implementation of artificial intelligence, an often heard statement is no AI without IA, or in full, no artificial intelligence without information architecture. In other words, to fully use the potential of artificial intelligence, the proper IA, information architecture, should be available. But what is this about? Well, a couple of years ago, we in the Netherlands conducted a survey to get clear what the impact of AI would be on healthcare. From this survey that was published, we found that over 90% of the respondents saw barriers for the development and clinical implementation of data-driven solutions, which artificial intelligence is one of. The most important reasons they gave for this were lack of expertise, the limitation of the IT infrastructure, and data accessibility. So this already shows that besides the expertise, so the education and training of people to make and to use AI, the IT infrastructure and data accessibility is basically also part of that infrastructure, can be a bottleneck for the actual implementation of AI in the clinical field. When looking at the findings of another report from 2020 from the HIMSS, the Healthcare and Information and Management Systems Society, and IBM about the journey to AI in healthcare, we see a comparable situation. When they asked how people would scale their current information architecture, based on the ability to support computationally intensive data analysis and artificial intelligence, they found that only 1/3 of respondents indicated to have the best possible solution or a largely workable solution. The rest of the respondents, as you can see here, were a lot less confident about their information architecture. Interestingly, in these responses, there was no relationship found with the size of the organization. So that leads to the conclusion that it's not the case that larger organizations have a better IT infrastructure than small ones. It's a kind of a mix. So there are also large organizations that don't have a good workable solution for implementation of artificial intelligence or other data intense software. Another question from this same research of HIMSS and IBM was how good the current information architecture is rated with respect to a number of different topics. Now, it can be perceived from this graph that's on the screen now that, for example, compliance with regulation and security have high scores and are apparently getting enough attention. However, there are also topics like performance, scalability, and ease of use that are lagging behind, and those are the ones that are very important for the development and implementation of AI. It gets even more interesting when we also look at the importance score respondents give to the same topics, because then we observe that the highest negative gaps are in the topics of cost efficiency, ease to use, and manage and high performance. So the topics that have high negative gaps are also the ones that are important for people that are dictating the status of their AI and are deemed to be the important ones. So that's kind of a wrong balance. We would like to see it differently. So we would like to see that also the gaps are small in these very specific topics. Now, before we go into some of those more specific topics, let's look at the global IT infrastructure that is needed for AI. In a paper by Dickey et al., they gave a very nice overview of 3 levels of complexity of AI. The paper is called Integrating AI into Radiology Workflow, and they start with a research-based setup. Here, the normal radiology workflow, which is in blue, is enhanced with a research packs that receives the output of an AI model and advanced viewers that are used to access these results and which are then only used for research purpose and not for day-to-day radiology practice. So the orange part is what's added to it, and it's really only the research domain. The second step they define is the production maturity level. In this step, the AI models are actually integrated into the workflow. So again, the blue part is the standard workflow. Now a green part is added, and here you see a small green box added to the router. So there is a routing of data to a server with an AI model running on it. So the images are sent to that AI model, and then the results are put back into the clinical packs. So now the AI results are available to all radiologists during day-to-day practice, but in this there is no feedback loop implemented yet. So they are just presented with the results and they will be part of their normal PACS viewing. This is the third complexity level that they sketch. So this is the highest maturity level. And here they introduced a feedback loop. They also call it the feedback maturity level. So in this setup, the AI model is in the bottom left. So again, you see that the router is forwarding the data to the AI model. But now you see something else. Also, a training server is available there. There is an annotation database. There's a viewer that is built especially for viewing the AI results. And that links again to the radiologist workstation. And you also see that there is a whole communication going on. So it's not just using an AI model, taking the results, putting that into your packs, and then viewing it on your workstation. No, it's about running an AI model, putting the results in your database, viewing those results, but also giving feedback. So when there is something wrong with the AI verdict, so you don't agree with it, you give that feedback, or you correct a segmentation that was done, you give that feedback back to the annotation database. So there's an updated version. You can use that updated version to do your training again in the training server, then have a new model, an updated model installed in the server, and in that way increase the performance of the model basically during use. So this is the feedback maturity level that they defined. The interesting thing is that you see a similar setup in the discussion paper on artificial intelligence and machine learning. That is shown here from the FDA. So they have a deployment model. So they say you deploy a model and then you have to apply good machine learning practices. Now that's what they show in this graph. And the FDA basically does the same. They say you have some kind of data selection and management. You use that to train and tune a model. You validate that model, and then you put that model into deployment. So you put the model into your clinical practice. And then new live data goes into that deployed model and what they implemented. So they call it the model monitoring. So they say, okay, you're checking constantly the performance of that model. And with that evaluation of the performance, you give feedback to the model. So the green line going up again is basically what we saw in the previous one, also the response of the radiologist or of somebody else who's checking the performance. And that information is put back into the model. We train a new model, that model is validated, and that's deployed again. So here you see a similar loop. And what they added here is that they also put in the safeguards in all the steps. So they say you have to do pre-market assurance of safety and effectiveness of your first model. And later on, you also have to review the pre-specification and algorithm change protocol. So when an algorithm change, you have to reevaluate the software as a medical device. So also these should be integrated into your whole environment. Now, after you pick the setup most relevant for your situation, so of those 3 different models that were defined, a first consideration to make is about data storage and management. Now, a useful model for this is provided by the Responsible Data Science Consortium, who have launched the FACT principle, in which the data science field, which also includes artificial intelligence, of course, is stimulated to be fair, accurate, confidential, and transparent. Now, they gave this diagram. You can find it on the website that I put down below there. And they show that there are that different databases from a diversity of systems have to be processed. So there's more information coming in than just from one single database. And in that step, you have to extract the data, you have to clean the data, you have, for example, to do anonymization or de-identification to obtain a database that can be used in the data analytics. So there are a lot of steps that you have to do. And those all have to do with that transparency, confidentiality, fairness, and accuracy. And this analysis procedure results that come out of that red block here, the data analytics. They should also be able to be fed back into the information systems, either directly or through human intervention. So that's the report, discover, mine, learn, check, visualize. That goes back into the results, and it goes back into the information systems again. So to organize something like this, your information architecture has a very large role. So you have to configure this not only by teaching your users how to do this, but also facilitating this within your digital environment. And then we come to the principle of FAIR. Because this scheme that is from the Responsible Data Science Consortium is very much in line with the FAIR data principle of findable, accessible, interoperable, and reusable data. This concept is also used as a starting point for collecting data for AI projects. And all in all, data collection is perhaps the most important part of the process of AI. And often it's also the limiting factor that we run into. Because large data sets of high quality and with a high degree of standardization are needed. And such data sets are not easy to bring together. And often also the information architecture is not implemented in a way that we can easily access the data or combine those different databases where that different information is found. The second consideration is about cloud or on-premise deployment of your AI structure. Because when we look back to that structure that was given by DigiKey, either one you're using, so this one or the more complex ones, you have to decide where those components go. They do not say what kind of choices you should make there, because that's a completely different question. So in this case, in the simple setup where we have that green server, this component should be placed somewhere. That could be on-premise or in the cloud. Or there could also be a mix, because later on, in the more difficult setups, we saw the different servers, the model, the training server, the database, etc. And we could split them up. We don't have to put everything on-premise. We can also put part into the cloud. And different components could even be housed at different cloud providers. So once you decide upon one cloud provider, you could easily also have different components at different cloud providers to divide the risk a bit. So this table gives you a brief overview of the pros and cons of cloud versus on-premise deployment for AI in healthcare. If we look at cloud, then the pros of cloud are scalability. Cloud providers can easily scale up or down resources as needed, making it very easy to handle fluctuations in demand. It's also cost-effective. Cloud providers often offer pay-as-you-go models that can save money in the long run, especially for smaller organizations, because you only pay what you use. You're not buying expensive hardware. A pro can also be access to expertise. They typically have teams of experts who can help organizations manage their IT infrastructure, which can be beneficial for organizations that lack that necessary experience or expertise in-house. A pro can also be security. They typically have a very well set up security and very specialized people that make sure that their systems are secure, and that can also help organizations to meet compliance and regulatory requirements. The cons of cloud deployment are that it's dependent on an internet connection. So cloud deployments typically require a stable internet connection, which can be a problem in areas with poor connectivity. And you could also say, well, it's also more prone to attacks if there is a denial of service attack, etc. So it could hamper the access to your information. There's also somewhat limited control. So the organizations that use the cloud have limited control over the underlying infrastructure when using the cloud services. So that can make it difficult to customize it to meet very specific needs. Besides the fact that clouds can be good for security, there are also risks for security. So there could still be security breaches if they are not properly managed. So, and that management could not only be by the cloud provider itself, it could also be by the people from the organization that is using the cloud. If they don't manage the systems properly, they could also cause security breaches themselves. Now, the cost is also sometimes a con. They have cost-effective pricing models, but there may be some hidden costs over time, such as data transfer cost or cost for additional services. One of the examples is, and we'll get to those, the use of those components later on, but if you're running on CPUs, then it's can be quite cheap. But once you fire up a graphical processor unit, so a GPU on a cloud service, then the prices go up, and then it can be way more expensive. So if we look at the on-premise, then there are also some pros. Control, when you have it on your own site on-premise, you have full control over everything. So you can customize it in any way you want. The security, you are responsible yourself for securing your infrastructure, so you have more control over the measures that are in place. There is no dependency on internet connection, so yeah, you typically have very fast connection to your own systems. There are also some cons for on-premise implementation. Scalability, it can be very difficult to scale up or down as needed, because yeah, you need to buy the hardware. If you need more hardware, you need to install it. Also, scaling down is even more difficult because you simply have the hardware. You cannot start selling it again and then buying it again when you need it more. So you can have a lot of time where systems are running idle without being actually used while you're still paying for them. So the cost is also one con. The on-premise deployments can be more expensive in the long run, as you must purchase and maintain your own hardware and software. And also with frequent updates, new processing units that come out, or new GPUs, you need to invest every time in new hardware. Expertise can also be a con. You have to get the expertise also in-house to set up and manage the full infrastructure. So that can also be quite challenging for smaller or medium-sized organizations to get that organized. And finally, as a con, the compliance and regulatory requirements. You're fully responsible for meeting all compliance and regulatory requirements when using on-premise deployments. And again, that is difficult for large organizations, but it can especially be a challenge for small and medium-sized organizations. A third consideration to think about is the hardware requirements for running AI models. When deploying AI in healthcare, it's also important to consider that hardware. And we have to be aware that the requirements can vary very much depending on the specific use case and the complexity of the AI model that is used. However, there are some general hardware requirements that are commonly needed for running AI models, and that's these 5 that are on here. So the CPU, the central processing unit responsible for executing instructions, and it's a critical component for running AI models. When you're doing less complex models, or when you are using more machine learning approaches, then a CPU is sufficient. When you go to more the image-based, so the real deep learning networks, then you need GPUs, the graphical processor units, and those are able to handle heavy computational demands of running AI models that work, for example, with imaging. So that's really for deep learning applications. Memory, most of the time we require to train a model a lot of data, but when we have a lot of data, we also have to have a lot of memory to get it to the model to train. So the GPUs and CPUs will access memory, and the amount of memory they have will dictate how much data you can use in one run, in one batch, basically, to train your model. Another thing is, of course, the storage. All the data also needs to be stored on hard drives or wherever to keep them safe. And that also can become quite large. And as we know, in the field of medical imaging, we really have a very large database that we need to store. Networking, that's also, there are high requirements on the networking, not only to get the data from the storage to the processor units, but also to get the data throughout the different components in the infrastructure. So we need to have fast network connections to get the data where it needs to go. In the previous slide, I mentioned the necessity of having GPUs installed. And this is a nice graph that shows why this is important, and especially when processing images. So here you see a graph from Microsoft. It's from the Azure environment, and they show here Keras and TensorFlow, and they implemented different networks. So the NASNet large, the ResNet 152, the ResNet 50, the MobileNet v2, those are all deep learning networks. And here you see the training in the Keras and the TensorFlow environment. So they were implemented in those two, and then they ran a task. And in the bars, you see the blue bar is 5 CPUs. The orange one is 1 GPU, green one is 2 GPUs, and the red one is 3 GPUs. Now, it's clear that no matter what type of deep learning network you're using, regardless of whether you're using Keras or TensorFlow, GPUs are always much faster when it comes to images. So the number, the bars, the height of the bars gives you the number of images that were handled per second as a throughput through the model. And you see that that's much faster with 3 GPUs than with 5 CPUs. So especially when it comes to images, GPUs are vital in the infrastructure running for AI. Now, finally, some considerations on maintaining and updating the infrastructure, because yeah, we can have an infrastructure running, but when it's running, you also need to keep it up. So in maintenance and in updating the environment, there are a couple of things that are important. Regular backups, both data and model parameters should be backed up on a regular basis to be able to recover when there is data loss or when there is a system failure. Software updates. Software has to be kept up to date. That can help address security vulnerabilities, for example, in the operating systems. It can also improve performance. On the other hand, one of the things you have to keep in mind with software updates, those of you that have built machine learning or deep learning models know that there are also updates in the packages that you use. And there it can be very difficult to use the updated packages because there may be deprecated functions in there and your software is not running anymore because of the new model update. So also in the whole development, we have to be aware what software updates are made, but also what version is used at what moment to train which model, etc. Monitoring, the performance of the infrastructure should be monitored regularly or basically constantly to be able to quickly identify and address issues. And version control. That's basically what I mentioned in the software updates also, but also for other softwares and models, you have to keep track of what versions are running at what moment to be able to understand how changes to the infrastructure are impacting the performance. For other topics in maintaining and updating are a test environment. So when you start using these kind of new tools as artificial intelligence, it would be good to start up with a test environment to be able to test new versions, new updates in a test data set to be able to determine that they work properly before you actually put them into the clinical practice. Incident response plan. So what do you do when something goes wrong? How do you respond to those incidents? Will you also report incidents with the software that is running? And how are you going to address issues that might arise? Continuous learning. That's a bit of a tricky thing. You should monitor the performance of AI models. And that's also something that is going to be one of the tasks for the vendors of those models. And they should be retrained when necessary. We know that there are all kinds of drifts that are influencing the performance of our AI models, and we need to adjust them to changes in the type of data that they get, or changes in the way we handle the decisions that are made. We cannot do the continuous or the retraining in clinical practice continuously. So we need to collect and monitor the performance, and then have a certain moment that we retrain it and deploy a new version of the AI in order to have them working properly also for new data, for example, that's coming in, or to be aware of future changes. Scalability is also a important point in the updating of an environment. You have to have a plan in place on how to scale the infrastructure as needed to handle fluctuations in demand. So that reflects again to what I said about the use of cloud or on-premises. With on-premises, you have to think about this much more yourself. With cloud environments, it's a bit easier to just ramp up your subscription with the cloud provider and get more capabilities within your infrastructure. So to wrap it up, I think that I started out and I showed you also there is no AI without IA. So IT infrastructure that you want to set up. So the type of infrastructure is depending on how you're going to use AI. Are you only using AI results in your PACS environment, or are you really developing yourself or giving feedback to the model? GPU availability becomes a requirement, cloud or on-premise, especially in our field of medical imaging informatics. And don't forget about maintaining and updating the AI IT infrastructure, because when you don't do that, then on very short notice, your whole environment will be, well, outdated. So thank you very much for your attention. And if there are any questions, I'm happy to take them.
Thank you very much, Peter, for this great overview. We have a question from Valentina Cuscio. I found the DICOM protocol to be working greatly inside the network of the clinics. When it comes to the transfer of DICOM data between the clinic's network and an external network where the IA server is, would you still use and adapt the DICOM protocol? How can the architecture be optimized to take into account firewalls and security concerns to enter the clinic's network? How do you make the transfer secure and encrypted?
Yeah, thank you. I think that's a couple of questions in one. The DICOM greatly inside the network. Yeah.
Yeah.
I think there is work ongoing within the DICOM committee to make so to adjust for AI, because of course when DICOM was started, there was no artificial intelligence whatsoever, so it's not something that is in there. So slowly you see the adoption also coming into those kind of protocols. So they yes, they are adapting the protocol. I think we should stick to using DICOM. If we lose that, then the whole ability to share and use data all over the world will be gone. So then it will be back to, what is it, 40 years ago, 30 years ago, when every vendor had his own data format, etc. And that's something we should try to avoid. So yes, the DICOM protocol should be adjusted to also comply to the requirements of artificial intelligence. Then the second question was, how can the architecture be optimized to take into account firewalls and security concerns to enter the clinic's network? Yeah, that's a very difficult question to answer like that. That's very dependent on the whole environment and setup. So there are ways to securely go through your firewalls, to have secure access to systems that are outside of your own firewalls. Sometimes using a DMZ in between two firewalls, so a demilitarized zone where you have the systems that connect to the outside world. So yeah, there are architectures that will take care of this for you. So yes, that is something that is possible, but it's really depending on your local situation and the way your network is built up. How do you make the transfer secure and encrypted? Yeah, that's also, that depends. There are several ways to have encrypted communication between two systems. Again, depends on the application, depends on the system you use, depend on the cloud environment that you're employing, etc. So there are a lot of different factors that will influence what kind of security protocols you have to use and what kind of encryption would be implemented. So you really should go talk to your own IT staff and discuss with them what is the best for your own environment.
Okay.
Thank you so much.
Okay, I think that with all that answers to one question, we fulfilled the time for the questions. So yeah, it's also time to close. So I would like to leave the virtual microphone to Pnar for the final remarks. And also thanking again Bayer for supporting us in this initiative.
Thank you very much. Thank you very much, Peter, again, for giving this great overview of the different steps. I think there's still a lot of discussion that we could have on the different levels and how to get there. And what we should be maybe try to go and take the steps forward to get there. Hopefully we can discuss that in another webinar. Yes, thank you so much, Bayer, for this for supporting these 5 great webinars. This was the last one of the series. I want to thank all of you for joining us, and I want to remind you for our annual meeting for this year that will be in Pisa on the 13th and 14th of October. So please join us all over there, and we can have great live meetings. And
see you in Pisa.
See you in person.
Thank you. And also for everyone can meet, see you next week in Vienna. Usomi will have a booth with Paola Rinaldi as master of this booth. You will have every news about our society and our future initiatives. And see you in Pisa, Italy, in the next winter, in the next fall. So.
Thank you, everyone.
See you again. Bye-bye.
See you soon.
Bye-bye. Thank you, Peter.
Thank you very much.
Bye.
Bye-bye.